There are two example problems I want to work on today. There's one point that I want to try to make clear. So these example problems, you're going to see similarities. And I want to point out a difference between them. So I'll try to make that as clear as I can. Other than that, it's just two more problems to work on and to understand for the exam. Yep.
Were you going to do practice sets for this upcoming exam?
Yeah, are there none up?
I don't think I
Okay, okay. Yeah, I'll put some up. Sorry, I have one. And we've done so many example problems, so consider those practice problems also. This exam is only going to be on this kinematics of a particle in a non-inertial coordinate system. No, we have an exam a week from today. And so let's go through sort of what's going on still with the end of the semester, okay? So we have exam 3 on Tuesday, I think that's the 8th. No, the 1st, I mean. Okay. And this exam is going to be only on one topic, particle kinematics. In non-inertial coordinate systems. So rotating coordinate systems and coordinate systems with accelerating origins. That's the stuff, we've been doing this stuff for quite a while. And then exam 4, which is at our scheduled finals time, is going to, so let's see. I haven't looked that up yet. Okay. At this time or at 11? Okay. So Thursday, May 11, 8 to 11. And it's just going to be our 4th exam, so you're not going to need that whole time. It'll be an hour and a half type exam. And this one is going to be on the stuff that we're going to do in the last 2 classes. And I'm hoping to get to the start of this today. So this is going to be on energy methods, and obviously we're not going to talk about this too much. There are a few practice problems that I have. So it's just an introduction to the idea of using energy for dynamics problems. This is what you focus on when you get into later dynamics classes. Okay, so one subject on each of these 2 exams, and that's the end of the semester. Then, well, any questions about either of these 2 exams? Okay. And then problem set 2. I think I said loosely due today, but you're welcome to hang on to it. So due today or whenever. But there's also going to be a problem set 3. That I'll get up this week. And that's due by the end of finals week. And that, you need to get it in by the end of finals week because I need to get the grades in. So that's what we still have going on. Any questions about any of that? Okay. Any questions about the problem set or anything you've been working on or thinking about? Either.
Yes, we did this like 4 times. I'm back down to 7 equations.
Okay.
I'm missing 2. Is there any way?
Missing 2 equations? Okay. So have you already calculated, so
I have 1 for, I guess, rod 1. I have 3 for rod 2. 1 for the disc. And I got 2 more using the relative motion. So I'm trying to figure out where I'm missing.
okay.
For each pin, so you can get 2. Because that was the first time I did it, but then I did acceleration from point to the about point. I got 2 there. But then the acceleration from that point to the origin, I just added the A, center of mass x and y to the equation because pin B or pin 2 is absent of that.
So if you call these A, B, C, and D, you're going to use
Did the velocity equation to come up with W1 and W2.
okay, good. So that's sort of separate. And I hadn't thought of this before, but Ryan noticed, like, you might think you could just throw those, like, the requirements to calculate those omegas. You could just add those as more equations and more variables, put it in your big matrix. But if you try to do that, you're going to get squared terms. So you have to do it separately. You can't calculate those omegas as part of your system of equations. I mean, really, technically you could do it, but you wouldn't be able to solve it as a matrix problem. You'd have to use some kind of numerical approach. You don't want to go there. So first calculate the omegas, and you can get numbers for those omegas. And then at that point, your constraint equations are going to be, so 2 constraint equations at B, and those are going to say alpha 1 cross R1, let's say R1 B plus omega 1 cross omega 1 cross R1B is equal to the acceleration of the center of mass of body 2. I need to number these. 1, 2, 3. So acceleration of the center of mass of 2 plus alpha 2 cross R2B plus omega 2 cross omega 2 cross R2B. Okay, so that's 2 equations saying that these 2 members have to stay together at B. Okay, and then 2 equations at C. And just as a reminder, why is there no A center of mass 1 in this equation? Because it's fixed here. Yep. And at C, you have, you could write this, since body 3 is fixed at D, you could write this as alpha 3 cross R3C plus omega 3 cross omega 3 cross R3C is equal to A center of mass 2 plus alpha 2 cross R2, this time we're going to C, plus omega 2 cross omega 2 cross R2C. Okay, so that's 4 constraint equations. Okay. And that's just saying the pin holds those two members together here and holds them together here. Yep. Any other questions about the problem set? Yep.
When you're calculating the omegas,
Yep.
what is body 2 really?
So when you're using just those relative motion equations, you can use any about point you want. So what you want to do in that case probably is you want to start at 3. Well, you could start at either end, but you know a point, you know. So to find the omegas, let's say we start at, we know D, okay? So the acceleration of C has to be equal to alpha 3 cross R, let's say, so this R is the vector going to C from D, okay? Plus omega 3 cross omega 3 cross R to C from D. Okay. And now you have a number for AC. Okay. So now you can calculate the acceleration of B, or you can express the acceleration of B. The acceleration of B is equal to alpha 2 cross R 2B from C plus omega 2 cross omega 2 cross, actually, I think the way I did it before was don't use the acceleration equations, use the velocity equations. Okay, so sorry about that. Let's get this out of here. Just delete all this stuff from your page and it'll look as good as new. Don't worry about that. So the two equations at C then are going to be the velocity. What did I? Oh, those were good. Okay. Okay. Okay, so the velocity at C is equal to omega 3 crossed with the vector going to C from D. Okay, and then the velocity at B up here is the velocity. So once you do this, you have numbers for VC, right? Now the velocity at B is equal to VC plus omega 2 cross the vector 2B from C. Okay. You can't solve this yet because you don't know omega 2 and you don't know VB. Okay. But now you can express VA as VB plus omega 1 crossed with the vector 2A from B. And what's the velocity of A? 0. So you can plug this in here, calculate omega 1 and omega 2. Does that help? Does that make sense, or is that confusing?
Yeah, that makes sense. So I guess just when you're looking at it, is it, so then later on, you talk about the body two rotate about in a B. You talk about it.
No,
So you get this
right.
omega 2 value, right?
Yeah.
And that's an angular velocity.
Yes.
And then so when you go to do your constraint equations, you use the angular velocity.
That's right.
Is that angular velocity? I mean, I guess.
Yeah. Okay, so that's a key thing about angular velocity and angular acceleration is that they're not associated with an about point. They just tell you how fast the orientation is changing. Okay? So once you calculate, so it doesn't matter what about point we use to calculate these, you know. We get these values for omega and alpha, and we can use those later when we change to our about point being the center of mass. Okay. So those are just properties. Those are just telling you like how quickly, the only thing those are telling you is how quickly you're changing, the thing's changing from this orientation to this orientation.
But I guess it just seems like when you do your constraint equation,
Mm-hmm.
like when you do your velocities, you talk about the velocity of C and the velocity of B,
Mm-hmm.
both have independent velocities kind of
Mm-hmm.
from each other. And then when you go to do your constraint equations, you look at the acceleration of B, and you talk about its radius, the rate, how far it is.
Mm-hmm.
But it seems like body two is in a way rotating about point C.
Body 2. Okay.
So then when you talk about the acceleration of B, there is a pin at C which is causing it to rotate. You take the radius from B to C?
No, just do it about the center of mass. So I guess really the way to think about it when you're talking about just the kinematics, nothing rotates about anything. Okay, there's no set point like this has to be rotating about this. There are things that are simpler because if a point is fixed, you know, the math gets simpler when you use relative motion equations because that thing has a value of 0. But those relative motion equations don't have any preferred about point. You can always use those for from any point to any other point. The only thing that has a preferred about point is rotational Newton's second law. Okay? When you do that, the rotational Newton's second law says you have to use the center of mass or you have to use a fixed point. But until that point, there's no preferred anything. You're just trying to make the math as simple as possible. Is that related to what you were asking about? Okay, good. Slightly, yeah. That's the best I can hope for. Any other questions? Okay. So here's the example that I'd like to work on first. I think I drew these at the end of class last time. Okay, so you have this plate that's rotating about these hinges. And if you have a rotation this way, let's say that the angular velocity is 50 radians per second. And the angular acceleration is in the opposite direction with a magnitude of 10 radians per second squared. And then up on top, you have a ball that's rotating around a circular path like that. It's going this direction. with an angular velocity of 100 radians per second and an angular acceleration in the same direction of 75 radians per second squared. And we'll say that the radius of this circle, which is the length of this arm, is 0.3 meters. And we'll say that the height of this rectangle, this plate, is 1.5 meters. And we want to calculate the acceleration of the ball at this instant. Okay. So so that we're all on the same page with a coordinate system, let's use a coordinate system that's oriented this way. So X, Y, Z, and you can locate it wherever you want. You can locate the origin wherever you want. Oh, and this angle is 60 degrees at this instant. Yes, that's right. And Z parallel to the line between these hinges, and the ball comes out of here along the x-axis. Yep. Okay, so see if you can make sense out of that. As you start to get stuff, compare what you're getting to the people next to you, and we'll go through that. And then, like I said, we're going to do another one that's similar to this, but we're going to have to approach a little differently, and I want to make it clear why. So first, where do you want to put the coordinate system? Yeah, I think that's the simplest. So put the coordinate system over here. So then you just have a rigid body, circular rotation around the y-axis. But then you have to deal with the acceleration of the origin. So the acceleration of that ball is going to be equal to the acceleration of the origin plus the acceleration of the ball according to the origin. We have to do a rigid body rotation to figure out the acceleration of the origin. So the acceleration of the origin is equal to alpha cross r plus omega cross r. Okay. That is, so what's the alpha in this case? Positive 10 along which axis? Z, yep. So 0, 0, 10 crossed with, what's the r vector? That r vector is just the vector going from the center of this rotation to the origin. So yeah, just 0, 1.50. What? Oh, yeah, that's right. And then omega is 0, 0, negative 50. Crossed with 0, 0, negative 50, cross 0, 1.5, 0. So the acceleration of the origin, I got negative 15, negative 3750, 0. Anyone get that same thing? Okay, and now we have to calculate the acceleration of b relative to the origin. And this is the one where we're going to use the fact that this coordinate system is rotating. So we're going to calculate this as the components double dot plus big omega cross p plus big omega dot cross p plus 2 big omega cross the components dot plus big omega cross quantity big omega cross p. The components double dot are the acceleration of the ball relative to that coordinate system. So this is just going to deal with that circular motion. And the components dotted are the velocity components of the ball in that rotating coordinate system. So to calculate the components dotted, you're just going to get omega cross r and what's the omega in this case? 0, negative 100, 0, right? That direction I drew is in the negative y direction for that rotation. So 0, negative 100, 0, crossed with an r vector of 0.300. And so you get 0, 0, 30. And the components double dot are alpha cross r plus omega cross r the alpha here is 0, negative 75, 0. R is 0.300. Omega is 0, negative 100, 0. Crossed with quantity 0, negative 100, 0. And the r vector is 0.300. If you do that whole calculation, I got negative 3,000, 0, positive 22.5. And so plug this into that full equation for kinematics in a rotating coordinate system. And the acceleration of p relative to the origin is negative 3,000, 0, 22.5, plus big omega dot cross R. What's big omega dot? Yeah, so for this example, big omega dot is this 10 radians per second squared. So that is going to be 0, 0, positive 10 crossed with 0.300. Then plus 2 times omega, which is 0, 0, negative 50, crossed with the velocity of the ball in the coordinate system. So what's that vector going to be? Well, that's the, or I guess the way I usually write it is as the components dotted. The components dotted we calculated here, so this is going to be 0, 0, 30. What do you get if you cross these two things? Nothing. You don't get a cross product if you, like cross product of two parallel vectors is 0. So this is going to go away. And then the last thing is omega, 0, 0, negative 50, crossed with the quantity 0, 0, negative 50, cross 0.300. Calculate all this, and I think you get negative 3750, 0, 22.5. You get something else? That's what I got.
Would you, that second term, 0, 0, 10, cross, you cross Z and X,
Yes, there's a 3 in there. That should be a...
the only thing is one.
Yeah. So that should be positive 3. And so I've been changing between B and P here, but come on. So the acceleration of B then is the acceleration of the origin plus the acceleration of B relative to the origin. So I got negative 3765, negative 3747, 22.5. Okay, so now calculate the force. Free body diagram of the ball looks like this. So there's a force on the ball by the arm. And then there's a, actually this isn't in line with the coordinate system. So there's some gravitational vector with a magnitude of 4.905. I'm going to just leave that out of here since the other forces are going to be so much bigger. But if you wanted to calculate this, you'd have to use a rotation matrix to deal with, you know, either to put this into our usual coordinate system or to put the gravitational, the weight force into our rotated coordinate system. And And so Newton's second law says FBA is equal to the mass times the acceleration and so then you can calculate the force on the ball by the arm is equal to about negative 1880, negative 1870, positive 11. And then to calculate, so I asked for the force on the arm by the ball. Then the force on the arm by the ball would be 1880, this is approximate, 1870, negative 11. Okay. Any questions about that? Okay, I would like to introduce the next topic before we stop. So let me just draw this problem. And I just want to point out something important about the difference between the problem we just did and this new one. Okay, so this is a related example. So say that you have this same plate oriented the same way. But this time, the motions are switched. Okay, so this time the plate is rotating around this way, 100 radians per second, and 75 radians per second squared. And the ball is rotating. Can you follow what I'm getting at here? The ball is rotating in a circular path this way. With an angular velocity of 50 radians per second and an angular velocity of negative 10. So in a lot of ways, this problem looks identical, right? And we're going to still use a coordinate system that's oriented the same way. So my question is, could we fix the coordinate system down here okay, What is my question? No. Could we fix the coordinate system up here on the ball? Let the coordinate system rotate with, say, the arm. And let the plate's rotation about its axis be the rigid body rotation in the coordinate system, and treat this problem the same way as the last example. Can you picture what I'm talking about? And the key to recognizing where you can put the coordinate system, I mean, so in some sense, yeah, you could, but you would never want to do it because you'd have to do crazy amounts of geometry to make it work in this way. Yeah, you'd have to do like sort of a compound circular motion thing. So what am I trying to get at here? The key is with these sort of compound motions, and usually these are going to be circular motions, but they don't have to be. One circular motion is always riding on top of the other one. And you can't just flip which one is sort of dependent on the other one. Okay? One circular motion is okay, so let's think about what's going on here. In this first example that we just did, if we have the coordinate system moving in a circle with the plate, right? That coordinate system is traveling in a true circular motion, right? And then there's relative to that coordinate system, there's a true circular motion happening due to the ball and the arm, okay? With this example, you can't set it up that way, okay? You can't, this arm isn't going through a true, like a simple circular motion. Do you see that? This arm is actually, so it's actually rotating in this circular motion while it changes orientation. It would be going through some kind of helical thing. Can you see that? And the reason that you can't break it up that way is because this hinge is riding on this, you know? So you can't flip the order. That's what I'm getting at. And that's usually going to be the case when you have multiple motions going on, okay? You have to identify which one is dependent on the other one. Does that make sense? I don't think I said that super clearly, but So the way that you have to set this up, and this orientation of the coordinate system is okay, you have to set it up with the coordinate system rotating about this axis, okay? And actually, probably an easier way would be, so if you had your coordinate system oriented like this, you'd have to do some rotations and stuff. So if you set your coordinate system like this, now, and your coordinate system is rotating around with the plate, okay? Now you do have a simple circular motion of the plate, okay? And in addition to that, a simple circular motion of the arm relative, okay? Yeah, so you'd have to do, I mean, you'd have an R vector that had an X and a Y component.
The reason why you wouldn't want to keep the y the same as we did before, in line with 60 degrees.
It's just easier to, so like when you had to define your omega of your coordinate system, this way it's just going to be 0, negative 100, 0. If you rotated it, it would have an X and a Y component, because that axis would still be going straight up, you know. Okay, so the order matters. I'll leave it at that. You're going to treat a thing like this differently than you're going to treat a thing like this, okay? Because the axis of this, okay, so those aren't the same thing, because the axis of this revolute joint changes as this position changes, right? Yep.
You could treat them the same, as long as you don't both. You could put a coordinate system.
Well, let's say that this thing is has the same angular velocity. Let's just think of angular velocities. So let's say it has the same angular velocity here that it has here, and here that it has here. The thing is, at the next instant, okay, so these are the same right now, but at the next instant, what is, let's see. So put your coordinate system aligned there. Okay. Now, no matter where this thing, goes along its hinge, okay, the top part spins around the y-axis, okay? So try doing the same thing here and see where the equivalent joint, this revolute joint, spins around, you know? So say you fix this coordinate system here, okay? Now, what's the axis of this rotation as this moves?
Right, yeah,
Okay.
I actually meant kind of locationally, they'd be in the same spot.
Yeah, well, the location, so I just did that to show what it's rotating with. The location doesn't affect
Right.
this.
Well, as long as you, I mean, maybe it's different
Mhm.
motion, but if you say, I'm gonna fix the coordinate system on the bottom point on the big body.
Yeah.
However, the big body's moving, that's how my coordinate system's going to move.
Yeah,
And, I mean,
right.
and they're both the same.
Yes, that's what you have to do. But then you're talking about, so this motion is the one that's equivalent to this motion, you know?
Yep.
And so you can't treat these two the same, and it's because of which joint is a passenger on the motion of the other joint. Yep.
Does it come down to you want to lock that one axis, maybe the Y, in one rotation?
Yes,
That's kind of
that's right. That's right. Yeah.
Anybody can do it.
So, yeah, I don't know. The more I talk, the less clear I'm making it. But you need to kind of look for that thing. Like, is one of these joints captive passenger on the motion of the other joint? And if so, you need to fix your coordinate system with the dominant joint. Okay. Okay, so we're not getting to the next stuff today, but we'll start that next time.